So now in this video, we're going to take a real short look at the 555 timer in bistable mode. So of course you got to power the 555 timer as always at 8 to positive supply, 1 to negative supply. For bistable, we disable pin 6 by putting it to the negative supply right there. When it comes to the signals, to control it, we have a low input to 2 in order to set the output high. If you give a low input to pin 4, that sets the output low. Pin number 4 is more powerful than pin number 2. If you hold pin number 4 low, it's going to keep the output low. Now, when it comes to the output, for my demonstration circuits, I use LEDs. When the output is high, it doesn't connect directly to 5 volts, so you probably lose a volt, maybe a volt and a half right there. But the red LED will light up there when the output's high. That's just the way the transistors are in there. When the output is low, it's connected to ground, and the blue LED will light up. So now in this short, we're going to look at the 555 timer in monostable mode. So you got to power the 555, 8 to positive, 1 to negative. Pin 4 is the reset pin. We don't want it to reset, so we disable it to pin 5. When it comes to the circuit right there, so the capacitor stays discharged. When we give a low input to pin 2 right there, that's when we start the cycle. That's when the capacitor starts charging and the output goes high. Once the capacitor gets to 2/3 of the supply voltage, it discharges through pin 7 right there, and the output goes low. And it waits until we press the button again. So the output is low until we press the button. It's only high for a period of time. So it's stable when it's low. That's where the monostable is. High input, red LED lights up. Low output, the blue LED lights up. Of course, you don't get the full positive supply voltage. You probably lose about 1.5 volts. So now in this short, we're going to look at the 555 timer in astable mode. Of course, you got to power it. 8 to positive, 1 to negative. Pin 4 is the reset pin. We disable it by putting it to the positive supply. And this circuit, first you start charging the capacitor through that path there. Timing resistor, diode, and the capacitor charges. Or you could go through 2 resistors by getting rid of that diode. But in any case, once it gets to 2/3 supply of the voltage, that's what these 2 pins look at, then it discharges through pin 7 until it drops down to 1/3 of the supply voltage, and it starts the process over again. So the capacitor keeps charging, output high, discharging, output low. When it comes to the output, when the output's high, the red LED lights up because we come from the 5 volts, but you lose about 1.5 volts in the process right there. You can use other voltages as well. You lose about 1.5 volts. When the output's low, then the blue LED lights up with this particular setup. So now one of the uses of the 555 timer that isn't normally taught, like just for basics, is as a Schmitt trigger inverter. Note that we're using 5 volts in this circuit, but 8 to the positive supply, 1 to the negative supply. Pin 4 we disable the reset pin by putting it to the positive supply. We have a trim pot here, and we can adjust the voltage, but you got some kind of voltage divider that's adjustable in some way. You get a high enough voltage, that sets the output low. You get a low enough voltage there, that sets the output high. These 2 pins monitor it. And therefore, whatever the input is, if it's high enough or low enough, it sets the output opposite. But there's a middle ground region where it could be in either state, between 1/3 and 2/3 supply of the voltage. And of course, when the output's high, if you're using 6 volts, you probably lose about 1.5 volts, so you should have about 4.5 volts coming out. But the red LED will light up. When the output is low, then the blue LED will light up in this particular circuit. So now we're going to talk about series LEDs, specifically the ones with 2 volts for forward voltage, like red LEDs. So there's a couple of reasons why you might want series red LEDs. First, you might want to light 5 of them with a single current path. And when you put them in parallel, you need to give each one their own resistor. But if you put them in series, they can all share a resistance because series components have the same amount of current flowing through them. You just got to remember that each one of them is going to drop about 2 volts if they are red LEDs. So you need a somewhat high voltage right there, 12 volts to light them. 2 volts will be across the current setting resistor, and we will get about 13.3 milliamps of current right there. There's the math. Remember, the resistor sets the current. And you may also just have more voltage than you want to handle, so you want to stack up LEDs to drop some of that voltage to help keep the pressure off of the resistor right there. So now in the last short, we looked at how 12 volts could light 5 red LEDs in series because they drop about 2 volts. Now if you have like blue or green or something, they're going to drop about 3 volts. So you can light about 3 of them in series. They will drop 9 volts, and then you'll have about 3 volts across the current setting resistor. There's a couple reasons why you might want to do this. First off, you might want to light 3 green LEDs, and you got 12 volts right there. So this is one current path right there. Makes it simple. If you wire them in parallel, each one needs its own protective resistor. Now, the other reason is maybe 12 volts is more than you're kind of comfortable working with when it comes to protecting an LED. So you just wire 3 of them to drop more voltage and to limit the current, the voltage across the resistor, I mean right there, so that it won't get as hot. You won't need as high of a value resistor to limit the current. And with blue and green LEDs, you don't need a lot of current, so 3 milliamps is fine.